Okay, in this video we are going to just do some example problems and we're going to move on to the binomial distribution case. So um, let's just do one more example, one more practice problem of using standard deviations and normal curves. If the average circumference of a 24-month-old male child's head is 19.182 inches, with a standard deviation of 0.557 inches, what is the probability of your child's head being between 21 and 22 inches? All right, so how are we going to do this? Well, first of all, just so you understand where this comes from, my child, when he was about 2 years old, was told he had a head that was within 5 standard deviations of the mean. And my wife and I looked at the doctor and said, because we understood what 5 standard deviations of the mean meant, we looked at them and said, try again. Um, so let's figure out what the probability of being between 21 and 22 inches would be. All right, so we're going to start off by probability of being between 21 and 22. Now notice I'm using x because these are the actual values. These are the inches. We have not converted to standard deviations yet. So now we're going to use our z-score. We're going to use our z-score that we talked about in the last video, which is your value minus the mean, and they tell us um, the average is 19.182. There we go, 19.182, with a standard deviation of 0.557. Okay, so now let's calculate what that is with our handy dandy little calculator. So will that be 21 minus 19.182? Take that answer, divide by 0.557, and we get that this z-score is 3.2639 and change. Okay, then we need the other z-score. We need the upper bound, which would be 22 minus 19.182. Excuse me. Let's clean that up a little bit. Divided by the same standard deviation, because that does not change. And so same thing, 20, but with the number 22 minus 19.182 divided by 0.557. And here we're going to get 5.0592-ish. Excuse me, 5.059-ish. Okay, so what that means is we are going to see what's the likelihood that your child, their head, if they're 24 months old and it's a boy, falls somewhere between, let's just round here, let's call it like that, is between 3.264 standard deviations and 5.05, well, let's call it 6. No, it's not. Let's keep it consistent. Let's make it 5, 9. We had 3 decimal places. We have 3 decimal places. Okay. So now, there is something in the world called a z-table. And some books use z-tables. And I just want to show you just a quick search of z-table brings up all these different options. And what they are, it's just a table of people who have calculated different values, different probabilities. And so if you want to use a z-table, you can. It really comes into play when you don't have access to a calculator. Instead of making us do it all with the formulas time, because what if you pulled out your calculator and you realized, oh, I don't have that formula in there? Well, there is somewhere in here in the distribution part of your calculator. So if we go second vars, now you'll notice there's the normal PDF and normal CDF. Normal CDF stands for cumulative distribution function. So what we're going to do is we're going to type in our bounds here. Our lower bound would be 3.264. Our upper bound would be 5.059. And our mu, again, this is normal, and notice how it defaults to that. Defaults to 0 and 1. So what we're going to go ahead and do is just leave that alone. And we're going to say paste. And what it does is it just fills in those values for us. So if you had an older operating system where it didn't fill it in, you'll notice what you type in. You would do that same normal CDF, and it'll put a parenthesis. So you put in your lower bound, comma, upper bound, comma, mean, comma, standard deviation. And voila, we get our answer. So what is this going to result in? What is this going to result in? We're going to result in our beautiful answer of 5.49 what is this e to the negative 4? Well, hopefully everybody has learned at some point in time up to this point that this is just scientific notation. It is the same thing as times 10 to the negative 4, which means shift your decimal place 4 places to the left. 1, 2, 3, 4. So add on 3 zeros. So that means our answer is 0.000549. So what does that mean probability-wise? That your child will fall somewhere between the third and the fifth standard deviation. It's going to happen very infrequently. So this is why we looked at the doctor and said, no, 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 go back and remeasure. Because if they told us we were outside the fifth standard deviation, that would be so abnormal, then you would look at your child's head and know there was something abnormal about it. You would just know it for sure. You'd be walking through the mall and people would say, "Ooh, what happened?" It would be very obvious. And so when we had an inkling, but we weren't sure, we knew they were wrong. We maybe somewhere between the third and the fifth, but definitely not past the fifth. That you would know it. You would just know. So they remeasured, and sure enough, we were at the third standard deviation, not the fifth. So nonetheless, just a little personal story, and why it helps to actually know what these things mean. All right. Nonetheless, so you can use z-tables to answer these problems if your teacher requires you to z-tables. I do not. You can use your calculator to help you do these problems. That is what I'm going to ask you to do. That being said, don't be dependent on the calculator. You need, and just typing in lower and upper bounds, and especially make sure you can convert things into z values. That is important as you go forward. So do not just become dependent on the calculator and say, because in that last screen, you saw that when you went to here, you could type in different mu's and different sigmas, different means and different standard deviations. That will not always be the case. So I will absolutely test you on your ability to change things into z-scores. Then once you do that, the integration or whatnot, that's up to you. But the key to me is getting things from the problem into z's, into standard deviations. Okay, now, next. A binomial distribution. How does that change things? Well, it changes it a lot, actually. So because when we're doing normal curves, because it was a continuous distribution, it makes sense to talk about all the space in between. But when it becomes binomial, that you can't have values in between. Like, so let's say our mean was, I don't know, 20, then 21, then 22, then 23. The space in between doesn't matter because it doesn't make sense because it's binomial. So what you'd be saying here is something to the extent of my graph would look like this. It would not have a nice smooth curve to it. It would be rigid. It would be stair-like, right? Whoops. Well, that's not what I wanted. So how are we going to handle this? How are we going to handle this? This would be 19, 19, 18, and so on, right? So we're going to say we want to find this area here, and then I need to find this area here. Well, you may remember this is Riemann sums from brief calculus, or a version of calculus you took. And good news, we're not going to go that route. What we're going to say, though, is instead of looking at it like this, what we're going to do is say, well, instead of doing left approximating or right approximating rectangles, what we can do is do midpoint approximating rectangles. So what we will do, wow, that was bad. Let's try that one more time. All right, we'll just move over. Hey, look, there's my mean now. Okay, what we're going to do is do midpoint approximating rectangles. So what we'll say here is my rectangle looks something like that, where I'm going to grab the height from the middle of it. And you'll notice there's a little overestimate, there's a little underestimate, because if I have error, I've got a little extra error here, I got a little extra error there, right? It's a little over, a little under, but the point being is the midpoint's the way to go. So if we were talking about, I don't know, scores on tests, well, you're only able to get even points, either get them right or wrong, kind of like a true false, right? So if you could get 20 right, would be the mean, or over here, the way I drew it, this here would be 21 points. Then the midpoint would be 20 20.5, right? The halfway in between would be 20.5. So going the other way would be very similar. So if 20 was my value and 19 was my next value, then the midpoint, assuming I actually drew that nicely, would be 19.5. So what we're going to do is say, all right, you have some probability that the person's going to ask about. Let's just call it A and B, okay? So you've got some values for A and B. And then what we're going to do is say, all right, I don't want the actual A value because I need to go to the midpoint of it. So instead of drawing my line at 20, I'm going to back it off half to make it 19.5. All right, so what we're going to say is if it's your lower bound, we're just going to subtract a 0.5. If it's your upper bound, we're going to raise it up a 0.5. And that's only because we're making the assumption that your increments are by 1. So you could have 20 points, 21 points, 22 points, 23 points. So halfway in between would be 0.5. So to say that if I had some kind of situation where my mean was 100 and then the next possible answer would be 105, the halfway in between would be 102.5, right? So therefore, my increments wouldn't be by 0.5s, they'd be by 2.5, since that's halfway in between my one step and the next. Good news, we're not doing any of these in this class. Everything we do will be one step increments, so you don't have to worry about it. But I just wanted to show you kind of why it's 0.5s. So we're just making assumptions: 19, then 20, then 21. Like, for example, another example would be a plane crash. You can't have half a plane crash, right? You either have 20 plane crashes or 21 plane crashes. You can't have 20 and a half. You can't sort of crash it. Okay, so let's do this problem now. When flipping 200 coins, what is the probability of getting between 100 and 105 heads? Okay, so 100 to 105 heads. So you see, there we go. Same setup as before, but now we're going to say to ourselves, is this a binomial? Can I get a half? No, you either get 100 or 99 or 98. You can't get a half. All right, so my lower bound we're going to subtract 0.5 from. So 100 minus 0.5 and 105 plus 0.5 because it is my upper bound. And it doesn't make sense to put an x here. That's kind of a little disingenuous. So, and we know our next step is going to be a z, is where our next value is going to be. So what makes sense to go here between x and z? Well, of course, that would be y, right? Because that's just logical, right? So what are we going to put here? What are we going to put for my y value? Because, I mean, I hope you guys can do this in your head, but what's 100 minus 0.5? Well, yeah, that's 99.5. And what's 105 plus 0.5? Well, yeah, that's 105.5. So now we're ready to change this into z-scores. Now we're ready to change this into standard deviations. So what do I need to be able to do that? I need a mean, right? And I need a standard deviation. Well, the good news, remember, with binomials, the mean is the same thing as expected value, and that was super easy to find. That was just n times p. And the standard deviation, once again, super easy to find. It's n times p times q square root. So what we're going to do is go into our problem and say, all right, what is our expected value? Well, we're flipping 200 coins. So 200, what's the probability of getting a heads? 1/2. So therefore, our expected value is 100. Okay, n times p times q. This would be our standard deviation. What is our n? Well, once again, that's 200. What's our p? That's 1/2. So therefore, I already got this. That part's 100. Then times the q. What's the probability of me not getting a heads? Well, that's 1/2 once again. So therefore, this is the square root of 50. Fantastic. And if you wanted to, of course, you could simplify that because, as I hope we all remember, this is how we simplify fractions. So this would be 5 root 2. Not fractions, how we simplify radicals. All right, so therefore, I now have my expected value of 100. I now have my standard deviation of 5 rad 2. And we are going to round our values. Let's round them to 2 decimal places. No, let's round them to 2 decimal places. That's what most z tables go to anyway, so it'll be very accurate or very similar to what our answers would be if we're using one of those. So what are we going to get here? We need our value of 99.5. Take away the mean of 100. And I always want you to ask yourself, does this make sense? 99.5 minus 100 would be a negative number, right? And 99.5 is below the mean, so therefore it makes sense for it to be a negative number. All right, so good. So then we're also going to have 105.5 minus 100 divided by 5 rad 2. Okay, so let's get some values here. Alrighty, 99.5 minus 100 divided by 5 radical 2. Let's close that up. And I get a z-score of negative 0.0707. And I said round to 2 decimal places, so we'll just call that a negative 0.07. Less than or equal to z, less than or equal to. All right, here we go. Hopefully you could do this in your head, which is 105.5 minus 100. Hey, that's just 5.5. Okay, divided by 5 radical 2. And that ends up being 0.777. And since we're running 2 decimal places, that'll just become 0.78. So now let's get this. You can either do it by integrating that equation, or you can use it doing the distribution. I'll do that. So let's go back to the normal cumulative display function, lower bound, distribution function, not display. So this would be what? My lower bound is negative 0.07. My upper bound is 0.78. Same u and sigma. So therefore, I'm going to paste that in. I'm going to hit enter. And we are going to end up with 0.31%, or 31%. And if you want to carry out a few more decimal places, we'll call it 0.3102. Great. So what does that mean? The likelihood of you be getting between 100 and 105 heads would be about 31% if you're flipping 200 coins. About a third of the time you're going to fall there, right? Which kind of makes sense, because if you're, somewhere above, just going from 0 to just about 1 standard deviation of the mean, you should be about 34%. So we're close to that. Our range isn't quite as big, but it's close. Very cool. All right, so then one more practice, and we are ready to roll, and we're going to do our checklist, make sure we finished everything, but I think we are good. So you try this one. Rolling 300 dice. What is the probability of getting of more than 60 dice? Showing the number 5 face up. More than 60 dice. All right. You can give it a shot, or maybe this one you're going to say, no, I don't want to do this one by myself. That's okay. All right, here we go. We are saying, what's the probability of getting more than 60? So therefore, x is greater than or equal to 60. Now, sometimes when we write it this way, some students have a hard time seeing, is this a lower bound or an upper bound? Well, so therefore, some students would prefer to write it this way, even though it's a little less conventional, but it's easier to see when you always have your arrows kind of pointing to the left, when you have it always the less than or equal to instead of a greater than or equal to sign. Because now you can clearly see it's a lower than bound. It's a lower bound. So therefore, if you were kind of thinking of it this way, here is my 60. Which way am I shading? Well, I want more than 60, right? So it's a lower bound. All right, so therefore, because it's a lower bound, the next thing we ask ourselves, are we ready to jump straight to z, or do we need to go with the intermediate step y? Is it possible to roll 60 and a half? No. So therefore, because it's a lower bound, we're going to minus 0.5 from it. So that should be a y now. And that's going to result in 59.5 is less than or equal to y. So now let's convert that into z-scores. How are we going to do that? Well, first thing I'm going to need is expected value. And we get that from n times p, and that would just be 300 times, what is the probability of getting a 5 face up on a die? The probability of getting a 5 face up is 1 out of 6. So therefore, that's a nice number, right? Thank you for doing that. 300 divided by 6, well, 30 divided by 6 would be 5, so that'd be 50. So therefore, I expect to get 50 sixes. Or, sorry, 55s. There we go. Now, this standard deviation would be equal to the square root of n times p times q. So that would be 300 times 1/6 times the probability of me not rolling a 5 would be 5/6. So therefore, this standard deviation would be what? Well, we already said 300 divided by 6 is 50. So I'm going to be left with the square root of 50 times 5/6. And what will that be? This is not going to be super pretty. So let's just get a decimal approximation, and we'll work with it from there. Right, let's see, the square root of 50. I don't like that extra parenthesis there. There you go. 50 times 5 divided by 6. So this is approximately 6.454972244. Now, if you're going to do something like this, I highly recommend keep the square root as exact as possible, but you will find most books are written with the assumption you're going to use a z-table. So because of that, z-tables usually only go up to 2 decimal places of accuracy. So if you keep your standard deviation like this, then your z's will have enough accuracy that when you go to type them into your calculator, you'll get the right answer. You'll get the answer that the book was expecting. So we are going to do 59.5 minus 50 divided by, what was our standard deviation? 6.454972244. Less than or equal to z, less than or equal to, what was our upper bound? Oh yeah, we didn't have one. We just wanted to know what's the likelihood that z will be bigger than that. All right, so let's figure out what this value actually is. So this is 59.5 minus 50 divided by 6.454972244. And we now have p, or sorry, this, p of 1.4717. And like I was saying, most books are going to only ask for 2 decimal places of accuracy. So you would see, even if this was rounded off a little bit, you would still end up with 1.47. So therefore, this will result in the answer that most books are looking for. So let's go ahead and go to our distribution and see how we're going to do this. There we go. Well, lower bound, 1.47. What's my upper bound? This is going to take some creative thinking. How are we going to get an upper bound? Because I don't have one. Well, let's think about the picture for a second. The mean is here. We are currently at 1.47 standard deviations of the mean, which we said was 0. And we want everything above it, right? So therefore, but I can't do that. The calculator needs an actual value. Well, do you remember, we've mentioned this before, that if we just go from half up, from the mean up, this would make 50% of your data. So what we could do instead is saying, well, instead of saying what I want, couldn't I figure out what I don't want and subtract away from the 50%? So instead of doing a lower bound of 1.47, let's just do a bound of 0 to 1.47. So a lower bound of 0, upper bound of 1.47, and everything else normal. So that is 4. Excuse me. So this area here is 0.429219086. So therefore, 0.5 minus that would be what we want. That will result in the black area. So therefore, I'm just going to do 0.5 minus my answer, and that results in, there we go. Whoops, excuse me, you go over here. So therefore, this number would be 0.0708. And most books, the z-table will go to 4 decimal places of accuracy. So therefore, if you just round to your 4th decimal place, you're more likely than not going to be fine. All right, so what's the big idea? What's the big idea here? We can now do a lot of the same problems we've done before using calculus. Instead of having to count these problems by hand, we can use this technique. This binomial works when it's defined as success or failure, right? And then the normal table works when your function is a continuous variable. But remember, all of this makes the assumption that your data fits the normal curve. So if the data you are working with isn't normal, you can't do this. You're going to need to come up with a different curve to work with it. So let's make sure we got everything. We have the definition of a normal distribution. We have the normal distribution graph and equation. We know how to use a standard normal curve to calculate probabilities, and we talked about how to use the binomial distribution with a standard normal curve. And in here, not only did we do the graph and the equation, I also showed you how to use your TI calculator. Alrighty, we'll see you in the next class, because this class is done. Well, unless I add anything on in the future. See you later.